last speaker of this session is Ben Heidenreich, and he'll be discussing about Orientifolds and N1.
All right. First of all, I'd like to thank the organizers for giving me the opportunity to speak here. This is based on some work with Iñaki Garcia Echeverria and Tim Raza, who's at Cornell also. So I'll be talking about some interesting new gauge theory dualities that arise when you consider D3 branes at Orientifold singularities. So why should we even think about this? Why are gauge theory dualities interesting? So of course the primary reason is that they tell us something about gauge theories at strong coupling. And we have another tool for that, of course, which is ADS-CFT. But in the case of gauge theory dualities, we have one distinct advantage, which is that we don't have to go to large n. There's no restriction there. So we can talk about finite n easily. And of course, these dualities sometimes prove useful for phenomenology. And of course, the kinds of gauge theories I'm talking about here, these 4D n equals 1 gauge theories, are of course what you want to study for phenomenology. And then the final point, which is somewhat important also, is that sometimes studying these dualities will tell us something about string theory. So let me start off with an example of how that could happen. So just think about n D3 branes in flat space. The gauge theory, of course, is n equals 4 super Yang-Mills, SUN. And if you study this gauge theory, you realize that it has some self-duality, some SL2Z self-duality, which is called Monton and Olive duality. So what does that tell us? So actually this implies, or you could argue that it implies, that type 2B string theory also has this SL2Z duality. This is what we call S-duality usually. Now there's a very strong statement, right, which is coming, or at least you're getting hints of it from the gauge theory. So let me talk about another example with some n equals 4 dualities. So we're just going to take the same system and add an O3 plane. Okay, we have a couple different choices here actually. So we could add an O3 minus, we get some SO2n. If I just put one extra D3 brane, I get SO2n plus 1. Or I can put an O3 plus and get USP2n. Okay. So how are these related to each other? Actually, it turns out that this gauge theory also has some kind of self-duality. But these two are S-dual. They're dual to each other. So this is also something that can be seen in the gauge theory. Now what does that tell us about string theory? Well, that actually just tells us what these O3 planes, how they transform under the SL2Z of type 2B string theory. So this O3 minus is just self-dual. So this O3 minus tilde, by this I mean an O3 minus with one extra D3 brane. And that extra D3 brane, of course, can't go anywhere because it's its own image. Turns out to be dual just to the O3 plus. So as a simple check, you can check that these have the same D3 charge, for instance. All right, so that's nice. Now, let me be a little bit more precise than that. Actually, these O3 minus and O3 plus actually fill out a triplet. So there's really two O3 pluses. They're just slightly different. Perturbatively, they're the same because they're one goes to the other when you shift the axion by one. But they fill out this triplet. And what's this graph that I'm showing for you here? What are these axes? Well, these axes actually just correspond to some torsion. So we have some homology group for our three-form flux. And in this case, it's just a Z2. So I have sort of on or off. So I get 4 different choices, and that's what correspond to these different O3 planes. So these O3 planes are classified by this discrete torsion, which is something that Witten realized a while ago. So keep this picture in mind because this will be relevant for what I'm going to talk about in a minute. All right, so the strategy is just that D3 branes are invariant under this SL2Z. Now, Orientifold planes may or may not break the SL2Z, and in the cases where they do break the SL2Z, that can lead to some gauge theories which are S-duals, which is potentially interesting. All right, so I've told you about how this works in a flat background, where we get n equals 4 gauge theories. Now let's think about something more interesting. So what if we put D3 branes at some Calabi-Yau singularity? Then we can get an n equals 1 gauge theory. Okay, so let's take a simple example, which is just C3 mod Z3. Now this geometry is a Calabi-Yau cone over CP2. So if I blow up the singularity, you have a CP2. But of course, to study the gauge theory, I'm going to look at the limit where the singularity is blown down. And if I put D3 branes here, then I'm going to get this quiver gauge theory here. So with these 3 nodes and the superpotential. And there's a global symmetry which is just geometric. So this SU3 cross U1 is just a geometric U3 that acts on the coordinates of C3. Okay, so now I want to orientifold this geometry. And I'm going to choose this particular orientifold, which has some compact O7 plane that wraps the CP2. Okay, so the orientifold, what that does for the gauge theory, you can just think of it as sort of folding up the quiver. So you identify by reflecting across this line. So this is sort of heuristic, but it turns out to be correct. And so the gauge theory that you get, well, I'm identifying the 2 halves, so I just have half left over. The half node is going to become some SO. And then this line, this bifundamental that gets self-identified becomes some antisymmetric. Actually, there's another choice. So there's this SO gauge group times SU with the antisymmetric. You can also make that an SP and this some symmetric. And both of these have a superpotential that's sort of like this. So these gauge theories, by the way, of course, this is a heuristic derivation, but these have been known for quite a while. So they were derived in the late 90s. All right, so here's just the same thing over again, and I can now add one detail. So here's those gauge theories, and now I can write in the R charge. And the R charge here is determined by anomaly cancellation. And then there's one extra detail here, which is just that there's some Z3 discrete symmetry. It's a baryonic discrete symmetry. That will come up in a minute. Okay, so now we can ask, is there a similar story before where we get some SL2Z triplet of dual gauge theories and maybe also some SL2Z singlet? All right, so as a baseline check, remember I told you that these axes here are really some discrete torsion. I should compute some cohomology group and make sure that it's the same, and in fact it is. So we still have some Z2 choices for discrete torsion for B2 and C2. All right, so we still have these options in the gravity dual, and now I just want to think about what could these gauge theories be? How do they fall onto this graph? All right, so what I can do is I can use 't Hooft anomaly matching, because if these gauge theories fall into some triplet, they should have matching anomalies because they're dual theories. All right, so remember I had these SU3 cross U1R global symmetries, so I just compute the anomalies. It's kind of complicated, but in the end it takes sort of a simple form. It only depends, in this case, on n times n minus 3, or here, n tilde times n tilde plus 3. So then you can see, it's not too hard to see that these anomalies do match if I take this particular relation between n and n tilde. All right, so now that allows me to fill out this diagram here. So I have some SP times SU group here, which is going to be dual to this SO times SU group here, with this particular relation between the rings. And then this is the same gauge group because it's perturbatively equivalent. And then there's this other one that's left out here, which should be self-dual. And actually there's a very simple check for that hypothesis, which is that if you take the SO8 cross SU12 variant, this is a gauge group that was studied back in the day because you can realize it in a compact example, and you totalize a few times, you have some type 1 theory. And then by type 1 heterotic duality, you get the same gauge theory, in fact, with some different stuff in the closed string sector. So the self-duality of this gauge theory is actually a type 1 heterotic duality, or can be realized that way, for the particular example of SO8 cross SU12. But then this seems to suggest that it should be self-dual for all n. Okay, so this is the basic picture. Now how can I test this idea? So I can think about some of the standard checks for gauge theory duality. So I can think about, for instance, are the moduli spaces of the two theories the same? Okay, so the operators in this case can be divided, as usual, into 5 minutes, okay, into some mesons and some baryons. And the mesons are very easy to match between the two theories, which is not surprising because they're really just D3 brane moduli. So it's telling you something about the geometry directly. But the baryons are more interesting. So rather than trying to match all of them, I'm just going to match the simplest ones. So I'll just take the ones with the least R charge. So in one theory that's this operator, and the other theory that's that one. And they both have some Z3 charge, some baryonic charge. So these have to match because there's nothing else around that has the same charges. Now if you enforce that they do match, you have to have their R charges be the same, and that's just going to reproduce this relation that we had before. Okay, so another thing we can do is we can check whether these configurations that are supposed to be dual, whether they have the same D3 charge or not. So just as a technical point, to do that I have to do some computation with exceptional collections to figure out what the D3 charge actually is. In this case, actually, I could also do it in F theory, but this is a bit more complicated. But in the end, these are the results I get. And for these to be the same, again, you get the same relation between n and n tilde. Okay, so now let me tell you about a few specific examples of this duality. So the simplest one, in a way, the lowest rank one, is between SU5 and SP6 cross SU2. And if you look at these carefully, you see that they both have a runaway vacuum. So at this point, there's not that much else that we can easily check because we don't have any holomorphic things to check, but they both break supersymmetry. All right, so let me go on to the next example, which is between these two gauge groups. In this case, this side turns out to be quite simple because this SP8 is S-confining. So I can confine it, and then I do some Seiberg duality on the remaining gauge group. I end up with an SO4 gauge group, which turns out to be it has a free fixed point. So everything flows to zero coupling. It's a simple description. And then I can see that there's a quantum moduli space, and it's parameterized by this baryon that I talked about before. All right, so then it would be nice to see the same thing on the other side. It's a bit harder, but I can do some specific things. I can turn on some vevs and try to match in some specific directions in moduli space. That's something that will be detailed in our paper, but it seems to work out. Okay, so for higher n, what I should expect, well, this is sort of a guess. It's hard to check, but you'd expect that there's still a moduli space because this is related by moving D3 branes on and off. And now there's going to be both baryonic directions and some mesonic direction, which is again related to moving the D3 branes on and off the tip. And then we should probably have an interacting fixed point at that point. You can see that from the R charges, that there should be an interacting fixed point. But some of this is difficult to check more explicitly. Okay, so now let me summarize. So I've argued for a duality between these two gauge theories, where I have some nice picture of them here, SO times SU with some antisymmetric matter, SP times SU with some symmetric matter. I've shown you some non-trivial checks. Actually, you could argue I haven't shown you all of the checks that we have. We have quite a few now, and Yaki will tell you about some more of them. So this is kind of a novel duality from the gauge theory perspective. You don't often see dualities between SO and SP, other than this n equals 4 example I already told you about. And as I said, it's quite closely related to this, except that it's n equals 1. But actually, it's also part of a much bigger story because, as I argued at the beginning, Orientifolds can break SL2Z, and you start off with some D3 branes and some geometry that can lead to some S-dual gauge theories. And in fact, you can go out and look and see what you find, and find that there are many other examples of anomaly matching. We haven't done all checks for these other examples, but there are many other examples of anomaly matching. So now just at the end, let me advertise Inyaki's talk. So he's going to talk, for instance, about you can compute the superconformal index. Yeah, I'm not going to explain this really, but yeah. But you should go. So.
Okay, excellent. Questions?
How difficult is to go closest to DP1? Sorry, go to DP1 or so?
Yeah. Yes, so DP1 is one of the simplest, the next simplest example.
And more or less, you can handle it like that.
Yeah. So this is a very nice example, and it's connected to DP0 by Higgsing. Yeah, that's very nice. Unfortunately, going to DP2 or DP3 is, and I'm not sure that the Orientifolds exist in that case. So we haven't been able to do that.
There was another question there, Timo.
Very nicely. Does this also have a nice interpretation in terms of F theory SL2Z? Can we see it in the fiber? What's going on?
I haven't thought about that, but of course, F-theory SL2Z is type 2B SL2Z, so there should be some way of thinking about it.
Yeah, actually the way I would present the string theory construction, we sort of lift it to large volume, lift to F-theory, and then the tree theory. So yeah, that's what the usual version.
Any more questions? I have a question. Can you generalize, I see there is very tiny sort of dimers in here. Can you apply this to general toric singularities in Orientifolds?
Yeah, you can do pretty much any toric singularity. It's not guaranteed that there will be dualities there, but it's easy to check. Yes. Yeah, so those are indeed tools that we use for these more general examples.
Just a comment. Also to non-toric form. So we have formulas in terms of exceptional collection. So
Okay.
yeah.
Okay, so let's thank the speaker again.